I am delighted to be able to introduce to you today our first external speaker of the semester. Lucas Vargas Zeppetello is coming to us from Berkeley, where he just started as an assistant professor. He got his bachelor's at Columbia in applied physics, and then did a PhD at the University of Washington in atmospheric sciences, like me, except he finished just in 2021, pretty recently compared to me. Then he went to Harvard and did a postdoc, and he recently won the Holton Award from the American Geophysical Union, which is extremely prestigious because he's a great scientist. Holton is the author of perhaps arguably the most important textbook in atmospheric science, just to give you an idea of how excellent Lucas is. So we're delighted to hear from you today. Thanks for coming, Lucas.
This on. Do people hear? Back? Can I get a thumbs up if you can hear me in the back? Okay, very good. Just let me know if that stops being the case. And please interrupt if you have questions through the talk. I'm not wedded to making it through any amount of this. So if you have questions, just find somebody with a microphone or put your hands up and I'll try to call on you. So I'm here to talk about heat waves and in particular trying to understand how extreme events, how extreme heat waves will evolve in a world that is warming. But before I start talking about heat waves specifically, I want to talk, oh shoot. Okay, let's see how this goes. I want to talk a little bit about what makes climate science unique. And to give you a sense of what I'm talking about here, I want to contrast, shoot. Okay, this might take some time. I want to contrast what I think we think about when we try to explain what science is to people, where there's an ideal science or an ideal idea about science where if I tell you that a rocket ship or meteor leaves the Earth with a particular position and a particular velocity, it will continue on an exact trajectory that we can find the solutions for in time. And if we do this experiment 1,000 times with 1,000 different rocks or projectiles, we will get basically the exact same answer. That's an idea about science that I think we have pretty firmly entrenched in our minds. And I'm going to contrast that with climate science. And the goal of climate science, in my opinion, is to understand patterns that are embedded within a very complicated system, and particularly a chaotic system. You can see this picture of Earth. There's a lot of processes happening all at the same time. They interact with each other. They overlap with one another. And there's a general state of chaos that sort of inheres in the planet's atmosphere. Now, how do we know things about chaotic system? And again, I contrast this sort of basic idea about precise predictions in time with something called chaos theory. So chaos theory, fun fact, was actually developed by an atmospheric scientist running experiments around cloud formation in the atmosphere. And the basic idea of chaos theory is that, while for this situation, if we put our projectile at one place at one specific time with a particular velocity, we'll get the same answer. In general, that's not true for chaotic systems. Very small perturbations in the experiment will lead to very different behavior through time. So you can see we start a particle at one place and it has this chaotic behavior where it gets into orbits and then transitions out of them and goes into a different state. Now, that doesn't mean we can't know anything about this system. So I contrast this sort of ideal situation where we have to know exactly what's going to happen at a particular time with a chaotic system where it's possible to know things about the character of the system without knowing what the exact situation will be in the future precisely. And that brings us to something that's going to be pretty important today, thinking about probability distributions. And so the way to relate this to this sort of trajectory diagram that I'm showing on the right is that we have places where a particle going through these trajectories is likely to be in time. So that corresponds to the peaks of this distribution, right? And then we have places where the particle is unlikely to be in time, which is in between these two sort of orbital periods or far, far to the sides of either one of them. So those are likely situations and unlikely situations. Now, how does this relate to heat waves? So before I start talking about heat waves, there's no set definition from a heat wave. We don't have an exact way to determine this is a heat wave and this is not a heat wave. What we do have is a long record of temperature variability, and we can generate probability distributions based on that. So these are three different distribution functions for 3 different cities. It doesn't really matter where they're from. And I've normalized them so that they can be directly compared with one another. And these all look pretty similar. So what constitutes a heat wave in this scenario? Is it, a particular separation from the average? So if 0 is the average, does 2 constitute a heat wave? Any threshold-based definition of a heat wave is going to be sort of inherently arbitrary. And I guess my big point here and what we're going to try to get through today is to learn about extreme events. We need to understand where the variations in temperature are coming from at a very general level. And so that's what we're going to try to do today. So an example of how this is going to work at a particular place in space. So I'm going to look at something that's called the Central England Time Series. Central England is a well-instrumented part of the world and has been for quite some time. So this is a time series that gives us daily temperature variability going all the way back to the 1770s. So every day we have a different value of average daily temperature. And so this is what that looks like. So it's kind of a mess. You can see the seasonal cycle. If you look carefully, we see up and down peaks every year. That's the hot summers and cold winters. And just as an example of thinking about how difficult it is to understand things about extremely high temperatures, we can look at the hottest day in this record. And if you can't tell, there's the arrow pointing to it. So this was June 19th, 2022, and it was 28.1 degrees Celsius. That's, again, average temperature. So we're not just looking at the hottest temperature of the day. It's average over the whole day. Before this, the previous record was 25.3 degrees Celsius. So this is a 3-degree change in the hottest recorded temperature in this extremely long time series. And I should note that in the first 100 years of the time series, so between 1772 and 1872, the record was 24.5 degrees Celsius. So about a degree cooler than the record as of 2019 that was then completely blown out of the water by 2022. So as another example of how to think about this, we can look at the number of times we observe a particular temperature. So now I'm only focusing on the warm season to try to get around some of that problems with the seasonal cycle. And what I'm showing here is on the y-axis, we have the number of times we observe a particular temperature. And this is on a log scale, right? So 10, 100, 1,000, going up towards 10,000. And then on the x-axis, we have temperature. So how many times are we observing a particular temperature? So if you look towards the center of the distribution, right, these are events that happen fairly frequently. We have 4,000 times that we saw a temperature, for example, between 15 and 16 degrees Celsius. So that's 4,000 observations up at the top. And now down here, we've got 1. So the argument here is that we can't really understand where 1 comes from unless we understand the entire shape of this distribution and how it may change as the global climate continues to warm. One other thing that I think is important for the future of heat waves is to look at the relationship between the average temperature and the maximum temperature for any particular summer. So looking through time, I'm plotting these as anomalies, so departures away from the first 100-year record of the time series. So this is the average temperature for summer in this time series. And you can see, year to year, it varies around. You can see, maybe if you squint your eyes, a warming trend. There's been about a degree of warming over the past 100 years in this time series, as I mentioned. And then we can look at the maximum temperature anomaly over the same period. And right away, you notice that there's a lot more noise in the maximum temperature component of the time series, but you can also notice that the maximum temperature in this time series is warming more than the mean. Now, why is this important? It's important because it suggests that the relationship between the maximum and the mean is not linear. If the maximum is warming more than the mean, it suggests that nonlinear impacts are in play for heat waves and extreme events as the climate warms up. So this is an example. We're going to try to understand the processes that are giving rise to these things and how they change with the climate. So the plan for today, first, what causes heat waves, right? I'm going to go through some physical arguments for why we have heat waves in the first place. Secondly, we're going to talk about our heat waves getting worse, and I'll show some observations that we can work through together. And then finally, what will heat exposure for human beings look like in the next 100 years? And notice that I'm switching terminology a bit between heat waves and heat exposure. I'm going to talk about the difference between those two things and why it's important in a little bit. But first, we're going to talk about what causes heat waves. And we're going to think about 3 different processes. So first, you can think about the global distribution of land and ocean in 2 dimensions. So this is thinking about the atmosphere as a 2-dimensional mixing machine. So if you have a warm ocean and then a land surface and then a cold ocean, you can think about places where the atmosphere is sort of conspiring to put air that was warmer over the land surface. That can get you a heat wave. So if we think about the atmosphere as sort of spinning around chaotically, this is a way that we can transport parcels of air with different properties over different parts of the land surface. So we call this atmospheric advection. And this all has to do with chaotic winds that transports air with different properties all around the global land surface. And again, if extremely warm air gets pushed somewhere where it typically isn't, then a heat wave can occur. That's the basic idea. This is all just simple mixing happening in 2 dimensions accomplished by the atmosphere. So how does this work in action? And to get a little bit more info on how this works, we're going to go to a seemingly unlikely location, which is Dome C in Antarctica. So this is a research station in the middle of Antarctica, or close to the South Pole. And in March of 2022, so just a couple months before central England got walloped with a record-breaking heat wave, Dome C experienced a day that was 39 degrees warmer than average for that time of year. Just to give you some perspective on that, it's about 0 degrees Celsius outside today. That's pretty average for, I think, this time of year, yeah? So that would be like if today outside it was 100 degrees Fahrenheit, right? So that's the kind of temperature anomaly that we're talking about here. And the authors of this paper that I'm going to show some results from claimed that this was the biggest anomaly in terms of departure from the average for a particular time of year that's ever been observed anywhere on Earth for as long as we have an instrumentation record. So this is a big heat wave. And just to see a little bit of what this looks like, these are the observations taken at Dome C every year before this event is shown in the gray lines. You can see there's a diurnal cycle. Every year is slightly different, but generally going up and down through time. And then in 2022, you just got an insane event that rocketed the temperature from normally down from -60 to -50 all the way up to -10. So again, not hot in sort of a standard consideration. It wouldn't be fun to run around outside in this weather, but just so much further away from the mean to be considered a heat wave in this sense. So how did this happen? And the answer has to do with atmospheric advection. So this is what we can do with weather prediction models, is trace parcels of air that end up in a certain place back towards their origin. And it turned out that for this event, almost all the air that ended up over Dome C in mid-March of 2022 was coming from a really hot continent, Australia, where there's a pretty significant chunk of desert. Normally, air cannot make it between Australia and Antarctica because there are winds going around Antarctica that make it very difficult for air to penetrate far into the continental interior of Antarctica. In this situation, that didn't happen, which is why this anomaly was so spectacular. This is really just to give you a sense of how effective the atmosphere can be at moving temperature around. So this is atmospheric advection in action. The second process I want to talk about, we've talked about 2-dimensional motion. Now I'm going to bring in vertical processes. So this is a schematic of what the atmospheric temperature looks like as you go up. So very close to the surface, the temperature decreases fairly rapidly, and that rate slows down a little bit as you get into the free atmosphere, and then temperature starts going up after you get above the troposphere and into the stratosphere. I'm not going to go into that right now, but this is just a general climate science point. We also have clouds. If you move clouds around in the vertical, you can change the amount of energy coming into the land surface. That can obviously influence heat waves. But what I'm going to talk about now is upward and downward motion. So downward motion in atmospheric science, we call it subsidence. Subsidence suppresses energy release from the surface. So it's basically like putting a lid on the land surface and trapping a bunch of energy down there, and that can create a heat wave. And subsidence can be driven by a couple different processes. Temperature changes all over in the vertical of the atmosphere. Specific weather systems can cause subsidence and trap that energy at the surface. And particularly in mountain ranges, you see a lot of subsidence effects due to the complex geometry of mountain ranges. So I'm not going to get into a ton about what causes subsidence, but the difference between subsidence subsidence is opposed by convection. So convection is transporting energy away from the land surface. It's turbulent transport up, and this is opposed by the large-scale subsidence. So we have this tug of war between processes, and what this determines is how effectively the land surface temperature can cool itself. So if convection wins, energy can be transported away, and we wouldn't expect a heat wave. If subsidence wins, that energy is trapped near the surface, and we can get a heat wave. And it turns out that there's a pretty clean relationship between these two things that determines how hot the surface can get in the presence of a particular upper level temperature anomaly. And so this is what this looks like. This is from a paper that came out last year that really makes a clean result of this. So you can see that for any given upper level temperature, because of the relationship between subsidence and convection, there's a limit to how hot the surface can get before convection is going to transport that energy away from the land surface. And it turns out that when you look at the observations, they tend to obey this limit, which is really nice. So we have an expression for the maximum possible surface temperature that can be obtained by a land surface, given this competition between downward and upward motion at the land surface. So this is kind of nice, but the problem is there's still a lot of explaining to do, because just having, in this case, warm air at the upper level of the atmosphere doesn't guarantee that there's going to be a heat wave. It just increases the maximum possible temperature that a particular land surface could obtain. So there's still some process that's generating heat waves preferentially. And that brings us to the last process, which is changes in soil moisture. So I mentioned energies coming into the land surface during the day, coming from the sun, essentially. That air can be used to convection, right? We can take that energy away by turbulence transporting air from the land surface up into the atmosphere. And that energy can also be used to evaporate liquid water, which doesn't change the temperature of the land surface. So if we channel that energy into evaporation, we're not going to be able to heat the surfaces as effectively, and there's less likelihood of getting a heat wave when you have a lot of water to evaporate. And so this is the way that I kind of think about this. Yellow denotes energy coming in from sunlight. If the soil is very, very dry, most of that energy is going to go into convection and heat the lower atmosphere, whereas very little is going to be evaporated. But in a wet soil, you have a different situation where a lot of the energy coming in is being used to evaporate the water, which doesn't change the temperature at all. But very little is going into convection, so the temperature stays relatively cool. So that's just a very schematic view of how soil moisture is related to heat waves. And it turns out that this is happening all over the world. So what I'm showing here is the fraction of extremely high temperatures. So all over the world, you can define a threshold. Every time we exceed that threshold, we call it an extremely high temperature. So what fraction of these events occurs when the soil is relatively dry? And the answer is quite a high fraction all over the world. And in particular, I'm going to draw attention. I think more people live in these two circles than live outside of them. So for a majority of the world's population, soil moisture is really key to the way that they experience heat waves. And then closer to home, at least from where we're standing in Ithaca, this is a region of intense agricultural production, and almost all the heat waves are occurring on days when the soil moisture is relatively dry. So there's a clear connection between these two processes, heat waves and soil moisture, based entirely on the partitioning of energy between convection and evaporation. So what timescales are these processes happening at? I'm drawing a line between things that happen on less than daily timescales, going out to a couple weeks, and then out to the monthly timescales. And just, this isn't sort of exhaustive, but in general, the vertical processes happen very quickly. They're tied to the cycle of solar radiation coming into the surface. That's how we get daytime convection. The 2D processes, the 2D mixing takes about 3 days to 2 weeks. They call these synoptic timescales. It's sort of related to how quickly the atmosphere blows through a particular place in space, how quickly a storm system persists over a particular place in space. Soil moisture has a bit of a longer memory. This you can get to about 2 weeks to 4 weeks out of soil moisture memory, just because it takes a long time to evaporate all the water that's contained in a land surface. And if you have more rain, you can continue to extend this memory a little bit for soil moisture. One thing that I'm not going to talk about so much is the relationship between things like El Nino or sea surface temperature variability and heat waves. And this does play a role. So this is a picture of how El Nino affects climate variability in the United States. Sea surface temperature anomalies can last for months on end, sometimes years. I'm not going to talk so much about how they influence heat waves, although they definitely do, and it's been shown to happen. But I'm going to focus on these sort of semi-shorter timescale processes so far. And the thinking about things in terms of timescales leads itself to the conception of atmospheric memory. And so what I'm going to show here are 3 different time series that have temperature as a function of time. The red line is going to show the threshold that constitutes a heat wave for these 3 particular time series. And in the first, there's no memory. So there's no connection between anomalies on a particular day and the anomalies the day before or the day after. And you can see this pretty clearly. We get 1 or 2, exceedances of the 95th percentile, and the day before both of those days, they're both relatively cold. So no memory in this time series. It's just random fluctuations. We call this white noise in climate world. The next one has a 3-day memory. So you can see here that the anomalies are less herky-jerky than in the first no memory time series. And you can see this even more clearly if I go up to a 7-day memory, where all of a sudden now we're seeing longer time scales of variation, and the extreme events tend to be more clustered together in time, right? So all of these time series has the same amount overall of back and forth. If you took the standard deviation of these 3 time series, they would be identical, but they look very different from one another. And these are examples of noise models. And these are really popular tools for understanding climate variability. And in particular, if a noise process has a memory, we call it red noise. And these are really standard tools for climate science because they allow us to incorporate that chaotic behavior that I talked about earlier with some kind of persistence associated with basically any geophysical system. Any geophysical system has some kind of memory timescale, and air temperature is no different. And in fact, if you look all over the world, especially at summertime temperatures, you get a memory timescale of about 3 days. And so again, in large part, that's just due to the fact that the atmosphere kind of blows through a particular place in space in 3 days. And we're going to see right now how a model like this that just incorporates some chaotic variability with some memory timescale can explain heat waves across the global land surface. And I can talk at the end about some limitations of this model as well. So all we need for our red noise model, we need a mean value. So I'm showing that in blue here. We need a magnitude for the noise. So this determines how much those processes that are happening in 2 and 3 dimensions and at the soil surface are influencing the temperature variability. And we need a memory time scale to understand sort of the inertia of the system and its resistance to change once it gets into a particular state. The other thing I was going to say that we can guess here in a model like this that the mean is going to change due to global warming, right? We know very well that the average temperature of this model is going to increase as the climate warms up. But the memory timescale and the magnitude of the noise, those are less certain. So we're going to leave those alone for what I'm going to talk about now and just consider how changing the mean value is going to change heat waves in this very idealized model. So going back to the probability distributions, this is the probability distribution of temperature anomalies, so departures from the average in this very simplified red noise model. And then I'm showing in the black line, this is the 95th percentile. This is what I'll construe as a heat wave in this particular situation. So if we have 100 days of sample, we'll expect 5 of them on average to exceed this. If we now shift the whole distribution, we just change the mean value. That's all I'm doing here. And you can run these simulations very easily on your computer as well. There's a very established equation for red noise. So we just shift, we get a different probability distribution that corresponds to a warmer world. That's all that's happening here. And the nice thing about this is that every sort of percentile of temperature, whether it's the mean, the 95th percentile, the 5th percentile, they're all changing at the same rate, right? So we're not prescribing any changes in the character of the extreme events. But given that, the mean and the extremes are moving at the same rate, but the number of record-breaking days by the previous climate's threshold. So if we think of 10 to 12 degrees, that constitutes a heat wave in this model. Now the number of days in the new climate that exceeds that threshold is going to increase exponentially. So what does this look like? If we go through and we run our simulations a bunch of times and we count the number of exceedances that happen as we continue to increase the mean temperature, we see exponential growth. So the black line shows the average across the simulations and the red line shows the spread. So again, this is just coming off of my computer. This is a very idealized model for climate change projections and heat waves. But we can see that events that used to be relatively uncommon, happening maybe twice per year, in a 4-degree world, you get almost a month of extreme events per year. So this is concerning. The new normal looks very different from the historical record in terms of the number of extreme events. going from what I would say would be a rare situation happening maybe once or twice a year to something that we experience for a month per year on average. So this is concerning, and it's sort of a good question when you come up with sort of a prediction like this to ask yourself, is this really happening? So to understand if this is really happening, we're going to go back to the Central England time series. And what I've done here is I've used the first 100 years to determine the threshold for what constitutes an extreme event. And I've just gone through the remaining 150 years and counted how many times that historical threshold has been exceeded. When you do this exercise, every year, there's a lot of noise, and you get different values as you go through in time. And then I took the decadal averages, so 10-year averages, which is what I'm showing in the black line. And you can see that for the last 30 years, we've about doubled the number of extreme events per year happening in Central England relative to the historical mean, which is exactly the projection that our simple model came up with. So this is kind of nice. It means that our simplified model that just takes into account a couple different processes has generated the same results that we're finding in Central England, where a 1-degree warming has resulted in a rough doubling of extreme events. And it turns out that this is not confined to Central England. So you can see that there are some summers where you get torched, right? And you've got more than 20 extreme events clustered together in one summer. I don't think I'm going to have time to get into this completely, but definitely ask me about it if you're curious later on. I'm happy to talk more about this. But now we're going to look across the world and see what's happening. So what I've done here is I've looked at 1,500 weather stations that have 100 years of data each. So we're getting the weather stations across the globe that have a large enough sample size that you can actually do this exercise. Unfortunately, these weather stations are centered mostly in the US and Eurasia for historical reasons that we can talk about later. So we're going to ask the same question of how much more common have extremes become. So again, I used the first 50 years of the record to define the threshold, and then the last 10 years from 2020 or 2013 to 2023 to define how much the number of extremes have increased. And you can see across Europe, we get anywhere from 80 to 200% increases in the number of extremes, so even exceeding the doubling that was predicted by the model. And across the globe, we can see that this exponential relationship between the mean temperature change and the percent increase in extremes seems to be generally verified. I mean, there's a lot of spread, and this is station data, so it's a bit messy, but I would say this is a pretty good success story of how much even a simple model is the one I put together earlier can explain the increase in heat waves as the mean climate warms up. So I think this is evidence that the number of extreme events is increasing exponentially as we would expect from this very simplified model of temperature variability. So what have we learned so far? We've gone through 3 processes that influence heat waves. We've talked about 2-dimensional motion, atmospheric convection, talked about vertical motion. This is subsidence versus convection, that tug of war. And we talked about soil moisture variations that partition energy between convection and evaporation. And I've also talked about this red noise model that combines these 3 processes and accurately predicts the observed rate of increase in extreme temperatures due to global warming. So what we're going to do next is talk about future heat stress and how we sort of predict how much future heat stress we're going to experience as the climate warms up. But I wanted to pause here for questions before I keep going. If anyone has a question, this is a great time. I've heard you get points for asking questions. It's amazing that no one's taking that gamble. Okay. Oh, very good.
Hello. So I saw on that map that while the vast majority of weather stations were showing more extremes, there were a few regions where there was actually significantly fewer.
Yep.
And they are bunched up in areas that are often surrounded by weather stations that have been experiencing more extremes. Do you know what the reasoning is for the reductions in those areas?
I don't know exactly. That's a really good question. I think another thing that you're getting at here, I thought we were having global warming, right? There's a whole section of these stations where the mean is decreasing, right? And it's kind of hard to tell by eye. Yeah, there's some. So I don't know what's responsible for these small scale noise. One thing that it could be is preferential steering of weather systems into these places that are having really increased chances of extremes. That would be something that I would describe as a statistical artifact, because you could imagine a world where it goes the other way and the other station warms more than the others. This is more interesting to me. Almost all of these stations that have decreased in their average temperature over the past 10 years are concentrated in the central US, where there's been an enormous agricultural expansion. And it's been documented that that has actually reduced the temperature despite overall global warming. So there's lots of timescales of processes happening here, but you're picking up on something that's really, really interesting. It's a good question. Yeah.
My question probably will be about like the location of this weather stations. Kind of like, I wonder, because we choose the locations not really by random, but like probably for some reasons. I wonder if that will influence the quality of the data and like probably generate some bias for the trend we have seen.
Yes, 100%. So there's a couple things in there. I think almost all of these stations that have these long records are situated at airports. The bias that that induces into these measurements is possibly substantial. Now, when this is the raw station data that I'm looking at, when you see a picture of sort of global trends that are drawn from station data, attempts are made to debias those samples. And we could talk about ways that that happens. Basically, you try to correct for the underlying land surface where you're measuring. So there's reasonable ways to do that. I don't think that'll affect the heat wave issue so much, but it does reflect changes in the mean. So for example, central England has urbanized dramatically since the 1700s. And that time series that I showed you, the trend in the actual observations is much more substantial. So they've debiased that time series to try to get out the global warming signal rather than sort of the urban heat island effect. So that's just one example of how this is typically done. It's a good question.
Just one more, and then we'll go on.
Oh, sure.
Yeah, real fast. So I saw, so on the previous slide, maybe one or two slides back, you were showing the time series of Central England and the 10-year averages. I noticed there's a downward trend in the mid-century. How do you explain that this isn't just a cyclical occurrence of going up and down, and that it's something beyond that, this 30-year warming trend that you were talking about?
How do you, oh, okay, interesting. So you're talking about, it looks like there's some back and forth here, right?
Yeah, and I just want to know how you establish that it's not just part of the back and forth.
So it's hard to establish that it's not part of the back and forth looking at a single time series, right? Mm-hmm. So I would say anyone who just looks at one single time series for one place in space and makes a big claim about it, that's not necessarily the right thing to do. But the point is that when we go out and look at the whole world, it also appears to be behaving like this. And there's no way that, like, basically you could explain this as, oh, this is just variations in climate if they were sort of anti-phase with somewhere else, right? So if this place was getting colder at a time when a place somewhere else was getting much warmer, that could explain it. But the point is that this is happening basically everywhere in a consistent manner. That's kind of the rationale there. But it's a really good question, because there are very long time scales of variability inherent in the climate system. So if you chop this record off at 1970 or something, so you defocus your eyes a little bit, this could just be wiggles in long-term modes of sea surface temperature variability, variations in El Nino, something like this. And that's a feature of climate variability, not a statistical artifact. So, the trends are real. The explanation for them could be different, but the consistency across the world is the sort of the key thing, which is why it's important to look everywhere.
Got it. Thank you.
No problem. I'm going to keep going because there's more stuff, but these are really good questions. So I hope you all ask more. So I'm going to get into future projections here. And there's a couple things that are important to get through. So projections of how much global warming there will be seems like an important issue. I'm going to talk about a very simplified framework to think about that problem. The relationship between global and local change, right? This is an issue if we're going to try to provide precise predictions that are relevant to people where they live. And then I'm going to talk about the relative humidity problem, which is really important for predicting heat exposure, as I'll get into. But the first things first, how do we predict emissions moving forward? So I think this is the only equation that I'm going to show. E is our emissions, so the total mass of carbon dioxide that humanity is emitting. And we're going to consider emissions as a product of three numbers. Now, again, there are a lot of ways to do this. This is one method that I am not a super expert in, but many people have gone through this exercise, and there's a big literature on this equation. So we're going to consider emissions as the product of the global population, so the number of people, the GDP of the global economy, so that's the amount of money that each person generates on average. So if you multiply P by GDP, you get total net output of the global economy in dollars, or whatever, money. And then F, which is the fossil efficiency of that economy. So that's mass of carbon per dollar that the economy generates. So this is an economic-centric way of thinking about carbon emissions, and it's called the Kaya identity, and we can use it to make predictions about how emissions will change in the future. You might be familiar with demographic projections, which is the P in this equation. The UN does those. The collaborator on this work was the guy who's sort of in charge of making these projections. I'll talk about the other two in a little bit. But so these are the emissions projections from this sort of simplified model of carbon emissions moving forward. And just to give you a sense, this red line here shows a doubling of CO2 relative to pre-industrial standards, which were about 280 parts per million. We're now at about 430 or something like this. So you can see at 2050, we have a pretty narrow range. That's just because it's closer in time. And then as we go out to 2100, there's a bigger range. I can talk about that in a second. But the basics that go into this model is a growing population. So most demographic models predict that by 2100, we're going to have over 10 billion people in the world. The GDP change is slightly more complicated. It basically assumes country level changes will over time converge to what has been observed in the developed world. I have a lot of questions about that assumption, and I imagine that many people in the room do too. This is the assumption that we made in this work, that developed countries will develop slowly, developing countries will develop quickly, and then develop slowly. That's sort of the rationale. And it has been observed over the past 40 or so years around the world. So maybe that's a little piece of evidence. The fossil efficiency of the economy. This is the big what if. We have very little predictive power over the fossil efficiency of the economy. So that is where most of the uncertainty in these projections are coming from. And the way the Kaya identity is structured, you can actually attribute the uncertainty. We didn't go through that exercise here. But okay, so now we know something about how our emissions are going to change. How does that relate to global warming? So the question is, even though you know your emissions, how much does those CO2 emissions change the global temperature? Now, this goes back a long time. This guy is Svante Arrhenius. In 1896, he came up with this number of 5 degrees Celsius for CO2 doubling. That was his prediction. About 100 years later, we had a report that was led by Jules Charny that put error bars on this estimate, and it came down a little bit. And in the past 50 years of climate science, we've eliminated the low bar on that estimate and moved up between 2.3 and 4.5. A really good number to have in your head is 3. 3 degrees warming per CO2 doubling. That sits right in the middle of this range. Maybe it's a bit conservative, 3.3 if you're wanting to go out to a decimal place. This has sort of been the standard for a long time. This is well constrained. We know this pretty well. But there are uncertainties. And so one way to look at this, we use climate model output just to say that there is a probability distribution of climate sensitivity. So most of the models sit in this range, and I've written this as degrees Celsius per 100 parts per million increase in CO2. So based on the climate model evidence that we have that's relatively consistent with our estimates of what past climates were like, it's possible for us to have a low climate sensitivity. And this would be good. It would give us more time to get away from fossil fuels without incurring a big global warming penalty. It's equally possible that climate sensitivity is high, and this would be the opposite problem, not so good. High climate sensitivity means we have less time before we incur a big temperature penalty. So we've got our emissions from the Kaya identity, and we have our climate sensitivity, or the global warming predicted from the models based on those CO2 increases. And now we essentially just multiply these two numbers together to get our temperature predictions. And I want to say that some of this is not fun to talk about. And there's going to be bad news that I just want to make that clear before we start putting this out there. So these are the global mean temperature predictions based on this model in 2050 and 2100. And so the bad news first is that there's almost certainty that we're going to hit 1.5 by the end of the century. And it's likely that we'll get there by 2050. And, based on where you start the count of what constitutes the pre-industrial global temperature, we might be there already. We're that close to 1.5 degrees Celsius. The other part of the bad news is that a 4-degree world, warmer than pre-industrial, is very much in play. So that's shown here in 2100. There's a pretty significant possibility, given the evidence that we have, of hitting 4 degrees of warming. So that's the bad news. The good news is that 2 degrees Celsius by the end of the century is roughly as likely as a 4-degree warming. So you can see that the probability associated with a 4-degree change is roughly equivalent to the probability of a 2-degree change. It's less likely, but not by that much. The other bit of good news, if you're an inherently optimistic person, is that much of the uncertainty in that green line, the 2100 projections, is tied to the uncertainty in the fossil efficiency of the economy. And the reason that's important is that we can't control climate sensitivity. That's a quantity that's baked into the physics of our climate. We can control the fossil efficiency of the economy, and that's something that policies can change, and so we can narrow the uncertainty associated with these temperature projections if we change the fossil efficiency of the economy. That's a reason for optimism, I think. So we've been through global changes, and we want to think globally, but act and predict locally. And the reason we have this saying in climate science that nobody lives on the global mean, so projections about global means are only as relevant as your capacity to translate them into what this means on the local level. So we want to connect the global averages that I just talked about to local changes in a climate. And this is where we have some good news science-wise. Well, good news from our capacity to do science-wise. So this is the ratio of local warming to global warming in the warm season. And climate models are pretty certain about this pattern. And it's mostly tied to how close you are to the North Pole and what your background soil moisture is. Again, that partition between evaporative cooling and heating is really important, even on these really, really long time scales. So what you can see here, basically what this is showing is that, if the world warms by 1 degree Celsius, in the northern part of the United States, it'll warm in the warm season by about 75% to a doubling of that. So it'll warm by 1.75 or 2 degrees Celsius in the warm season, given a 1 degree of global warming. So this phenomena is known as land amplification. It just has to do with how much the land can evaporate relative to the ocean. So climate models agree fairly well on this. And so what that means is if we know the global warming, we can predict the local warming, which is nice. So we already have a way for these two things to talk to each other. But now we run into this problem of relative humidity. I love this picture of this guy just hosing himself on a really hot day. Why is relative humidity important to temperature projections and heat stress projections? So we cool our bodies by sweating, right? We need a gradient of water across our skin and into the atmosphere to do that. And if the air has more moisture in it, if the air is more humid, our natural sweat mechanism is not effective and we can't cool ourselves as efficiently. And so changes in relative humidity are really important. And relative humidity is basically just the fraction of saturation of the atmosphere. So basically how much water could you fit into the atmosphere relative to what's in there already. So on a 100% relative humidity day, it's basically raining is what this means. So the heat index is the tool that NOAA uses and OSHA uses to send out heat stress warnings. So if you've ever gotten a heat stress warning on your phone or something like this, it has to do with what the heat index is at the place that you're at. And so you can see going along up top, we get warmer and warmer temperatures, and that translates into warmer and warmer colors, which indicate different levels of danger, nebulously defined. These are not like concrete thresholds. This is just what NOAA uses. And then you can see if you pick a particular temperature, so just look at, let's say 92 degrees Celsius, right? 92 degrees Fahrenheit, excuse me, and 40% relative humidity, you're in extreme caution zone. As you go up in relative humidity, you pretty quickly get to extreme danger. And extreme danger, at least according to NOAA and OSHA, is like you need to get in AC immediately because your body can't tolerate those kinds of events. So this is the heat index, and it depends on how relative humidity changes. And this is where we actually do get some luck from the climate system, because over a large fraction of the land surface, climate change means the relative humidity will decrease. There's a physical reason for that I can talk about if folks are interested in. So this is good in the sense that we'll be able to sweat more effectively, despite the fact that the temperatures will be higher in most places. Where this isn't true is where this turns into a problem. Places like sub-Saharan Africa and the Indian subcontinent, we're projecting increases in relative humidity. This is the opposite of what we'd like to see from a health perspective. These are places where there are a lot of people who are relatively unable to adapt and that already experience fairly high temperatures. So this is a real concern, as we'll see in a second. So the caveat of all this is that the climate models are less certain about this as they are about the temperature pattern. So this can be taken with a slight grain of salt, even though we have some basic physical arguments for why the drying, the brown color, should be happening. I mentioned this already. There's some pretty important regions where relative humidity appears to be going up. Okay, so we are now going to combine everything we've talked about so far today. If my clicker will go, great. Okay, so what we're going to do is use the heat index and go through the observational record and just count how many times on average per year do we exceed this dangerous threshold across the world. So we have global observations for this over the past 30, 40 years. And we can do the same exercise for extreme danger. How often do we go above this threshold, just in the ambient environment? So just keep in mind that when these things were being formulated, they were for indoor workers, people working in just like extreme environments, steam, stuff like that. So how often do these temperatures happen in just the ambient environment? And so in the historical record, this is the number of dangerous days per year that were observed between 1979 and 1998, so a 20-year period. Now, there's a lot of information here, particularly about the subtropics. So sub-Saharan Africa, the Indian subcontinent really sing out, places in Australia and South America as well, places where dangerous days are a feature of the seasonal cycle. So in some sense, people have adapted to experiencing a large number of dangerous days each year. There's work adaptations that go into this. There's a big literature on adapting to high temperatures. But in general, this is a sort of, maybe you get a month, maybe 2 months. It's a seasonal phenomena, exceedances of these dangerous thresholds. So just keep that in mind. Dangerous days, they happen a season at best, right? Or at worst, I guess. Extreme danger really doesn't happen that much. It's difficult for the atmosphere as currently constituted to sustain really, really hot and really, really humid air at the land surface for any meaningful length of time. So you can see that basically outside of these regions that are heavily influenced by the warm waters in basically the Arabian Sea, really, really rare occurrences. So what about the future? And again, we're going to do bad news first. So we're going to look at projections in the 4-degree world. So this is a 4.3 degree warming. This was the 95th percentile of those probability distributions. So this has, according to our model, again, a 5% chance of becoming reality in the future. And right off the bat, looking at dangerous days, again, these were seasonal phenomena in the historical climate. Now we're talking about things that encompass most of the year across most of the habitable or habitated world. So again, over 150 days in the Indian subcontinent, sub-Saharan Africa, parts of the maritime continent, South America, even parts of the United States are going to be, more than just seasonal, but multiple months of the year. Where this gets a little darker is looking at the extremely dangerous days per year. And again, across large sections of sub-Saharan Africa, the Indian subcontinent, parts of China, and even in the US, these, again, are days that just simply don't happen in the contemporary climate. And now we're seeing them not just become rare, but becoming fixtures of the cycle, much in the ways that dangerous days currently are. But again, the sort of lethality of the extreme days, we don't know what happens when a large population is exposed to events like this, certainly not regularly. So this is a real cause for concern. Now, I'm going to show a plot of what happens in a 2-degree warming. So again, this is unlikely, but still possible. And this, you can see more of just an amplification of the pattern that was already there. I would argue that this is not as much of a fundamental shift away from the historical observations as the 4-degree world. So again, there are increases. It's becoming more and more of the year in a lot of these places that I've discussed already, but certainly not the vast majority of the year spent at these temperatures. And then in the extremely dangerous days, we get the same thing. Still a rare event almost everywhere across the world. The subcontinent has some work to do. And I'm in touch with folks there who are doing active heat planning around the results from this paper that have just been fascinating people to work with, who are really thinking very far ahead on this issue because they know that this is going to be a real problem moving forward. So how I wanted to close today is just by saying that our actions are really important. So I just contrast what, in my mind, is a policy failure, which is a +4-degree world where extremely dangerous days become fixtures of the climate for most of the global population, from the Paris Agreement, where we keep that at bay. And this to me seems like a real binary between these two options. So this is, it's fork in the road time around this issue. And I think it's important to be clear-eyed about the possible consequences of going past this, which is why it's really important that we understand what could happen if large groups of people are exposed to temperatures like this on a regular basis. So just as a summary, I've talked about multiple processes that act on different timescales to influence heat waves. We've talked about a really simple theory for temperature variability and how that can influence the changes in extreme events through time with global warming. And then I've also discussed a little bit about how future heat exposure is linked to anthropogenic CO2 emissions and the choices that we make today and why they're really important. I have more stuff, but I'll leave it there and I'm happy to take questions for now. Thank you. Angie, do you want me to call on people or do you want to? Okay.
I'm really interested in hearing more about the people that you're planning with, and especially like around these sort of equatorial nations where there's a lot of economic disparity. Like, how do you ensure that people who don't have access to a lot of resources are able to afford like safe climate environments, I guess?
That's a really good question. And we're at a point where, so first of all, I am not an expert on planning or solutions. And I think it's important to have that disclaimer for a physical scientist. But the people who I'm talking to are very aware of the difference between what you could call triage, of just like treating the symptom, you know, when an ambulance comes, right? They do triage work. You have a problem, you take care of it right away. That looks like enhancing the capacity to provide water to people, to put up cooling centers where like the most vulnerable people can come to have access to stuff without cost to themselves. So that's one chunk. The more interesting thing to me, thinking long-term, especially given the nature of the changes that are on the table at this point, is like, is it going to be required to restructure how people in these places live? I don't know the answer to that. But the folks that I'm working with are thinking about, you know, what can we do with our cities, with our work habits, with our ways of interacting with one another to actually provide resilience on a much, much longer time scale. Again, I don't know what the right way to think about this is other than provide more resources for people who don't have them. But thinking in these different time scales is starting to become more prevalent, which I think is really important. I don't know if that answers your question, but that's what my experience has been.
Hi, I'm wondering if you about the Dome Sea incident, if you think that was a heat wave caused by like climate change, or if it was just a random anomaly that occurred.
Yeah, I would say that was a random one. You know, it's hard to give precise attribution numbers for a lot of different kinds of events that happen in the atmosphere. And the more extreme event, is, the more difficult it is to actually make those precise claims. So I would always encourage people to have a grain of salt with anything you read about this event was, 96% driven by climate change. It matters what your metric is. It matters what system you're looking at. That event likely would have happened had we not existed at some point along the line, right? From my point of view, that was a, crazy atmospheric anomaly that was probably made a little bit worse by the fact that we've warmed the planet by at least a degree. But, we're talking about a 39-degree anomaly there. So it's just, there's a little bit of a ratio difference there.
Hi, I was really interested in like a few slides back when you were looking at the 4.3 degrees Celsius warning.
Yeah.
I was curious, can you explain like what happened to South America? And there are like so many more dangerous days per year compared to like the slide previous.
Here?
Yeah.
And then we're going back here, right? Yeah. Right, okay, so historically, very, very small. And then with a 4-degree warming, not so small. It goes back to the same issue, right? About why extreme events increase exponentially rather than linearly. And it all has to do with like, okay, if this, I don't know if people can see. If this is my distribution, right? And right now, an extremely dangerous day is like out here. It doesn't really happen. But if I shift, all of a sudden, there's a lot of weight of that distribution that all of a sudden entered a regime where it previously wasn't. So it's the same process that gives rise to that exponential increase in the number of events. But it's important to understand how close to these thresholds the global tropics are currently situated, right? So like if this is the extreme danger threshold, there's a lot of places in the tropics that right now, they're just outside of it. And that's why it's so enormously consequential, even when we move the mean just by a little bit. I hope that answers your question. Okay.
Hi. I was interested in knowing better if the models, there's an effect of like deforestation or wildlife fires or things like that, that like natural disasters that have an increase in how fast things will change. Because I know you talked about the impact of fossil fuels, but like I'm from South America. I remember when the fires in the Amazon were happening, it was like very impactful in my region down in Brazil. So yeah, I was just wondering about that.
Yeah, so the models are, so first of all, this is not, the models don't have those kinds of scenarios embedded in them. And it's not clear that their representation of them is very good. And so that's a real area where the effects can be highly nonlinear without necessarily knowing about it beforehand. And I would say that the ecological part of all this is something that's a big problem for global climate models and something that a ton of people are actively, trying to get at. We were just having a conversation about this before I walked over here. Like, how sensitive are these ecosystems to temperature change? Like, we don't know. And there's a precautionary principle thing there to say we should assume that they are very sensitive, which, seems to be bearing out a little bit in South America. But as for whether that's in these projections, no. So in that sense, they're conservative.
Hi, I was just a little bit confused earlier on in the slideshow because we were talking about how like heat waves are more common in like dry soil areas. But then if there's more dry soil areas due to like, more climate change or more like agriculture drying out the soil, like does that necessarily mean that there would be more so-called like dangerous days with like humidity in those dry soil areas? Or like how does the humidity come into play if there's a drier soil, or is that caused by like more weather events or something like that?
That's a great question. So there is a trade-off between warming temperatures and drying. And it's, people have looked at this over a couple different regions. I think that the main, you can go online and see how the sensitivity of the heat index changes with different variations in temperature and humidity. Once you get up to higher and higher temperatures, the temperature effect is stronger than the humidity change. But again, we don't know these things for sure. And it probably depends on how people are acclimated and all this. So there's all these things about, potential regional variations. But in general, the consensus of the public health community seems to be that temperature is the most important thing secondary to humidity. who that's true for, what underlying health conditions might alter that, who knows. But you're right to point out that differences in land use practices could put their fingerprint on this stuff, absolutely. And the degree to which that's in here is not much.
This is kind of similar, but is like the reason why like sub-Saharan Africa is so prone to like all the extreme like temperatures and things like that, like especially if it gets really warm, is it due to because it's like really dry and stuff like that, or is it something else?
Yeah, it's the same thing of
Yeah.
just being close to those thresholds to begin with, right? So you see this kind of like, if you think about, okay, here's the equator, right? The places that are like the most concerning from this perspective are 20 to 30 degrees north of the equator. That's what climate science people call the subtropics, right? So those are the regions where it's very hot and very humid for a good fraction of the year. Whereas right on the equator, it tends to be a bit cooler just because there's more rain there. Whereas in the subtropics, the rain is much more seasonal. That's the sort of hand-wavy explanation for what you're picking up on. Yeah.
When you were showing your first maps of like the historical record, I noticed they were from like a couple decades ago.
Yeah.
Do you have any that show what it's like in the past, I don't know, 3 or 4 years?
Yeah, so I'm working with undergrad who's doing her thesis on this. We only looked at India and the observational record. It's in line with these predictions essentially. So the number of exposure is going up. We don't. It's difficult to do for these extremely dangerous days just because they don't happen that much. So we needed a long record to sort of get the base statistics. So it's hard from that perspective.
I'm curious, since you said that humidity is also projected to increase rapidly in these regions, would the rate of extreme rain events also increase? And how would that affect the heat waves? Would they be happening at the same time?
Probably not the same time for extreme rainfall, but Angie's the expert on extreme rainfall, but there's some evidence that extreme rainfall is increasing over India, but there's a lot of these changes that are working in the same direction. So I think extreme rain would potentially make the heat waves worse because if rain is highly concentrated in particular spells, it also runs off quicker. The storage capacity of the surface is sort of inhibited. If the rain, you can think of it as the atmosphere gets it all out of its system, and then it runs off because the surface can't contain it, and then it doesn't get replenished. So you could think about more extreme rainfall actually leading to more heat waves because the soil dries out quicker in the long-term average. But whether or not there's going to be more extreme rainfall over India, I'm not super sure, probably.
Do the predictions in global temperature increases account for the positive feedback loops that occur and then contribute to the rises in temperature?
What do you mean by positive feedback loops?
Like, for example, ice melting and then releasing the permafrost that causes increasing temperature.
Yeah, so the Earth system models have all these kinds of feedbacks in them. Their representation of permafrost specifically, I can't totally speak to, and that's a big uncertainty for climate models in terms of their emissions. But the other thing about it is, another big one of these is just the global land surface takes up about 1/3 of humanity's carbon right now. And in these Earth system models, I don't have more space around the board, but basically we don't know if that number is going to go up by 10 or 20% or become zero and the land is going to start spitting back carbon into the atmosphere. So that's just a big uncertainty in the carbon feedbacks in the system. And again, given that uncertainty, that's all part of that spread in climate sensitivity that I showed. So all those processes that you're talking about work together to influence this, right? So if you get more dramatic wildfires, ecosystem destabilization, you're going to move yourself into this realm of climate sensitivity, where if you have a more stable system than you think, and for some reason the ice shelves are resilient and the land will take up more carbon, you're going over to the smaller values. So that's the difference.
I was wondering if soil structure was taken into consideration at all with soil moisture content and seeing how that evaporation rate changes.
I'm sure there's some stuff in there around soil structure, and certainly different plant communities are in these models as well. So they are they are quite sophisticated. The degree to which they're representing reality is another problem. But yeah, there's a lot of stuff in these land models that is pretty sophisticated. But again, how well it does and how much it matters, I don't know for sure.
Hello. Going all the way back to the concept of atmospheric advection, it made me think about the thermohaline belt. And I was wondering if during your research, you saw any correlation between the distribution of heat waves or changing climate patterns that correlated with changing thermohaline belt behaviors.
Yeah, so I didn't look at that specifically. It's hard to disentangle things. So the thermohaline belt is an oceanic circulation that happens at very low timescales. And it's really difficult to disentangle possible changes in thermohaline circulation from just background changes in climate. And so I would go back to this baseline behavior of we expect an exponential increase in heat waves driven by global warming, however it's accomplished. And whether the thermohaline circulation is going to put its fingerprint on that, it still remains to be seen and is ultimately embedded in this same question about possible positive or negative feedbacks that influence climate sensitivity.
Hi, thank you for your lecture today. Right here. Over here. Thank you for your lecture today. During the lecture, you said that there is almost certainty that we will hit plus 1.5 degrees Celsius by the end of the century, likely by 2050. I was wondering if that was if we are functioning kind of in our normal state as is in terms of policy, or is that even if we do somehow, like hypothetically, implement a lot of policy initiatives that help the environment and combat climate change. And then also when it comes to the potential of increasing by +2 or +4 degrees Celsius, would the same proposed policies that have been kind of suggested for the potential crisis of a 1.5 increase help combat that? Or is there more that we need to do with a higher temperature projective?
Okay, big question. So I'm going to answer the second part first. There's a ton of policy proposals that all have to do with reducing carbon emissions. Any one of them, the atmosphere doesn't care where the carbon comes from or how it gets put out. It just cares what the number is. I think that's a really important distinction to make because everyone hears so much about, my favorite policy solution is this, my favorite policy. Ultimately, the number is what matters, not the way it is accomplished. So I think the same kinds of things that are proposed, there's no more radical thing. It's just the quantity of policies that get put forward and ultimately acts all together to get that one number as far down as we can. The question about 1.5, and I know that this is a bummer because there's a lot of rhetoric out there about 1.5 that really started during the Paris Agreement. In some sense, I think it was slightly irresponsible of people doing the Paris Agreement to put so much out there around 1.5 because, first of all, I was a junior in college when that number came out. And I remember I was just getting interested in climate science. I was talking to people about this stuff. Nobody seriously believed that that was going to happen, given the amount of warming that's already baked into the system, right? And I mentioned that it's possible, depending on where you start your calculation, right? Because somebody brought up these long-term wiggles in the system, right? I'm now going to commit a cardinal sin and draw over something I drew already, but here. If this is, 1700, right? Whatever temperature record we have, before this, we're sort of trundling along. Maybe this is, 1900. Now we start going up, right? So depending on where you draw your average for what constitutes the pre-industrial, you're going to get a slightly different answer. So it's based on that, it's possible that we've exceeded that threshold already. So then there's really nothing we can do. But to answer your second question again, the same policies that are, at least as far as I'm concerned, going to keep us below 2, get us as close to 2 as we possibly can, are important, depending on how much we decide to blow past that number. And yeah, I'm sorry to be a drag. I know that number is out there and means a lot to a lot of different people, but I also think it's important to be really clear about the consequences of what people have already done. got one right here.
I mean, similar to that question, you said that there's a chance between 2 degree, the
Put your hand up.
same chance. Oh, sorry.
Yeah, there you go.
There's the same chance for a 2-degree-Celsius world versus a 4-degree-Celsius world.
Yeah.
Kind of what factors do you see would indicate whether or not we're going to be a 2-degree-Celsius versus a 4?
Like I said, it's all about, I mean, at least I think this Kaya identity is really helpful in this sense because you can break down, you know, what's the low-hanging fruit, right? You know, changing these are sort of the main controls, right? And again, I feel free to disagree with this. I am not invested in this being the way we think about this problem, but you know, what's the easiest thing to control among global population, global economic growth, and fossil efficiency of the economy? I would argue it's the fossil efficiency, right? There's low-hanging fruit. We can get this number to be less. To me, that's where you start. And the lower you can get that down, the less chance we have of going over this 2-degree limit. And again, it's not even helpful to think about things as the limit, as we see, right? It's a continuum. Like, you know, there's nothing, yeah, anyway. Yeah.
Hi. So going back to the topic of climate sensitivity, in an earlier lecture, we were talking about how recent models are predicting like higher climate sensitivity based on factors like cloud cover and aerosols. And I wanted to ask, what kind of timescale do you think we'll be able to more accurately determine climate sensitivity, and what kinds of data will we be like looking for to refine that prediction?
Great question. Well, eventually, if at some point we stop increasing the carbon dioxide in the atmosphere and it stabilizes, and then we wait a long time, then we'll know, which is not a satisfying answer. How will we get better at understanding what climate sensitivity is doing? You know, because as you point out, there's so much that goes into those estimates. There's all these different kinds of forcing agents. Getting the historical temperature time series is actually a really important component of this, because if you're going to tell us how much you've changed the temperature, you need to know what your baseline was. So a more in-depth understanding of what's happened in the past is also important. Again, this doesn't necessarily answer your question, but there's improvements to all kinds of different sections of these climate models that could, in theory, help us to constrain climate sensitivity. That is sort of the general theory of how climate models have been developed. The problem is they're going in the wrong direction because the spread keeps getting bigger every generation that comes out. So whether this is a good strategy for getting better at estimating climate sensitivity, I don't know, but ultimately, I would say it's not, you know, we know what the reasonable range is, and we've seen how the reasonable range plays out given the current uncertainty in emissions reduction. So in some sense, it's an excellent science question, and it's something that we should be interested in because we're concerned about the fate of our planet. But I don't think it's a question that requires a really specific answer in order to motivate policy, certainly. We're long past that point.
Time for one last question.
Hi, I was wondering if the governments in sub-Saharan Africa and India, like the areas most affected, have been made aware of the research, and if so, what plans have they been looking to implement?
Nobody's called, but thank you for laughing. Like I said, you know, people are taking extreme heat seriously. I think the major hurdle is that we don't have, I can sit up here and make projections about the heat index until I'm blue in the face. It doesn't really matter until I paint a coherent picture, or somebody paints a coherent picture of what events like this actually mean to people. And that's where the public health folks are really coming in handy, because they're trying to say, okay, if we have an event like this on a large scale, how does this matter to people who are living in these cities, which is what I'm in talks with the folks who are doing the South Asia research about.
One more thanks for
Thank
coming
you.
and joining us. Thank you. Awesome.
Thank you.
Thank you.
Yeah.